about the subject, you know, you say, well, how long does it take? How long does it yeah, you guys did sodium bicarbonate, where you take sodium bicarbonate, basically baking soda, and mix it with some sort of acid, acetic acid, vinegar, could be HCl, and it fizzes. How long does it take? How long does it take to finish doing its thing? Well, that might be a good example. You're like, you know, you need to wait a little bit, okay? But a lot of times we think if we mix reactants, it goes to form products. But it takes a certain amount of time to work through and to go from reactants to products. So we're going to talk about what we call reaction rates. How long does it take? So the study of reaction rates is sometimes called the kinetics. Kinetic energy is energy associated with motion. Okay, kinetics is how fast is that thing going to go? Okay, how fast does it happen? So I'm going to add to this slide, and you might want to also. Of course, anytime you see change in physical science, we use the Greek letter delta. So I'm going to see a triangle. Okay, so reaction rate, I'll put RXN rate is equal to change in concentration. So delta, change in concentration, divided by change in time, or the time over which that concentration change occurs. That's reaction rate. Change in concentration divided by change in time. We're going to talk generally about reactants go to form products. But does this make sense that as this proceeds, and not all reactions, chemical reactions, go from left to right, but we're talking about the left to right kind, your reactants will decrease, the concentration of your reactants will decrease, and the concentration of your products will build up or increase. Makes sense? Here's the one thing, and remember when we did the gas laws, we talked about those five, the pressure, volume, number of moles, temperature, 4. Things that, like, if one goes up, the other goes up, one goes up, the other goes down, okay? And we said that if they have a direct relationship, we would say that one is proportional to the other. One goes up, the other goes up. In this case, actually, this is an inverse relationship. What this says is that, and I like to do it the other way around, as time increases, rate will decrease. As time increases, rate goes down. It's kind of how I think it is. It's the same thing. As time increases, rate goes down. That means all reactions slow down over time. True. All reactions slow down over time. And if I were to ask you, you're kind of quiet today, but you might say something like, well, yeah, they slow down because there's less and less reactants to react. That's true. Okay? The rate at which a reaction proceeds from reactants to products slows down over time. We'll talk more about what this K means later on. And I printed these out for myself because I'm going to refer to them later. If you want to put your finger there and dog ear, you can. So one thing right off the bat is anytime you see, I'll put it up here. Anytime you see this means molar concentration. I don't think we've talked about that yet. Molar concentration. So R is reactant, P is product. So what we should see is our reactants decreasing the molarity and our products increasing the molarity, right? Let's see if that's what the data looks like. So this would be what we call our initial. Does that make sense? Time 0. Initial molar concentration. We have all R and no P. Makes sense. After 5 seconds, notice our reactant has decreased, our product has increased. After 10 seconds, after 15 seconds, after 20 seconds. Now, here in a minute, we're going to actually do some little calculations because I told you that rate or reaction rate, it's all the same thing, either one, is change in, and now I'm going to go ahead and say change in, I said change in concentration, change in molar concentration of the reactant or the product divided by change in time. Where actually all we got to do for these reactants is, I'll do it up here, is we could do it over this time interval. For instance, from 5 to 10 seconds, we could see that we could take this number, it's final minus initial, so we take this number, this molarity minus this molarity, divided by 5 seconds. Divide that over that time interval. That's all we're talking. That's how that works. Reaction rate, you could pick any two. We could come up with the reaction rate from the interval when it started to 15 seconds. We could do that. We could take, in the top, it'd be the 0.045 minus 0.2. In the bottom, it would be 15 seconds. So you can pick any interval you want. But it's going to be slowing down. It's like chasing something that's slowing down. Okay? And I bet you, hopefully you'll buy this, you can track the decrease of the reactant or the increase of the product. And actually, I'm going to show you how this works. You'll ultimately get the same reaction rate. So the red here is the decreasing amount of reactant. The green here is the increasing amount of product. And I'm pretty sure it's consistent with the data on the previous slide. This is this. Now the stoichiometry here, it's been a while since we talked about stoichiometry, actually happens to be a 1-to-1. So this means for every mole of reactant that is consumed, 1 mole of product is formed. It just happens to, it won't always be. So if, let's see how I can do this. So for instance, we could look at these. A minute ago, I said we can look between time intervals. This would be what? Let's see, 10, so this would be 2 seconds. Over 2 seconds, we could take the change in concentration divided by the change in time, and that would be the rate for that time interval. That also would be the slope of this line. That is the slope of that line.
Excuse me, is the R and the P the opposite, like reactants to product and product to reactants?
It's just going one way. R is always going to be the reactants, as I have it here. It's red, and P is the products.
Yeah, that's right. I was just
Yep,
but
it's
they're
over
the
there.
same thing. Okay.
Yep. You got it. We could look at it over, what is this? 2, 4, 6, 8, 10. So this looks like 2, 4. This is time interval 4 to 6 seconds, right? I could compare these two slopes, and to me, the steeper the slope means the faster the rate. And actually, we have a slower rate here. It's slowed down. We have less of a slope. It's slowed down. Okay, and I don't know if you're convinced of that, but it is changing. It's getting less and less. I could go ahead and get a reaction rate, like I think I might have told you a minute ago, by going over the first 10 seconds. And this is what it would look like. I could go over the whole enchilada for 30 seconds. And you're going to get different rates. I don't know if you're familiar with the tangent, the concept of tangent. So this actually, a tangent line, a line that's tangent to the curve, because this is kind of a curve, actually that is the rate. So this would be, what, 10 seconds, and this is kind of cool. Instead of like an average kind of rate between 2 times, this is going to be what we call the instantaneous rate. We aren't going to do any tangent lines. This would be the instantaneous rate at 10 seconds. So, a lot of times when we get started, and sometimes I don't take the time to talk about this, but we are going to be talking a lot about initial rates. Initial rates, instead of kind of rates down the road when we get started in this unit. But does that kind of look like an initial rate? It does to me. And this would be a rate at what time? Maybe 10 minutes or so. Kind of, that looks like to me a line trying to be tangent to this line. Doesn't look like, maybe it's supposed to be 12, but it looks a little short than 12. Because rate is change in concentration over time. Slope is change in concentration, in this case hydrogen peroxide, over change in Y, which is time. See how that works? So we can follow how much, we can follow either the reactant or the product. We can. So you're going to have to be able to kind of go with that. So if we go back to, I think we're going to be picking on this. We can choose any times. So, like for instance, we could choose when this says T2 or T1, this could be, 15 seconds and 10 seconds, or 15 seconds and 5 seconds. We choose any time. That'll be change in time, and then we have to choose the corresponding reactant, or excuse me, the corresponding, reactants, and do a subtraction to get the change. We could concentrate on the products over here, okay, and do a similar thing, come up with the rate. Now, and I think we'll get to this. We're doing good for time. Let me close that door because I have it. Because sometimes I get down the road and I don't try to make this distinction. These are not reaction rates per se. This is the change. This is the rate with regard to R. This is the rate with regard to P. It may or may not be the reaction rate, and I'll kind of show you what I mean by that. All right, so let's pick on R, going from 0 to 5. Okay, so 0 to 5. Right, 0 to 5. So our delta R, or a change in reactant, it's always final minus initial. So it's that final, 0.121, minus the initial, 0.200. You guys follow? But this is where it came from. And notice that if we're adding or subtracting, we can go ahead and do parentheses and do units outside the parentheses to kind of help alleviate some of the hand cramp. So as we're subtracting, we round according to decimals. So our delta R is negative, and the negative does come along, negative 0.079 moles per liter. So that's going to be in the numerator of our rate with regard to R, reaction rate, change of R. So what's going to go in the denominator? It's a change in time. 5 seconds, that's it. Oh, I see I'm doing the math here though. So math, so it's final minus initial. So the final time was 5.0 seconds, initial time was 0.0 seconds. Yep, 5.0 seconds goes in the bottom. Then we just divide. And I wouldn't call it reaction rate yet. And like I said, this will make more sense. So I would keep my delta R over delta T is equal to negative 0.079 moles per liter divided by the delta T, which is 5 seconds. Oh, looks like it's like 5.0 seconds. You're allowed 2 sig figs. And so you end up with negative 0.016. And then units would be moles per liter. And then also in the denominator would be seconds. Sometimes, I don't know if I did it in my my homework, but does this make sense? You could sometimes call this molar per second. It's the same thing. All right. Well, we could pick on the product, and I'm looking at the sheet here. And for the product, to me, it went from final minus initial. So the final is 0.079 minus initial is 0. So I got .079. Units would be moles per liter. Again, 5.0 seconds. And it's the same thing, right? But in this case, it's a positive. 0.016 molar per second. Yeah. So doing that, let's see if our rates, we said it should slow down, right? Let's see if it slows down over time. So we just did this one from 0 to 5 seconds. And we came up with a negative for the reactant, a positive for the product. If you go to the next interval, 5 to 10 seconds, see it slowing down. And your reactants are always going to have a negative rate of change with regard to the reactants, and your products are always going to be positive. But now that's not the rate. I'm going to tell you what the rate is. Slowing down yet? 10 to 15 seconds. 15 to 20. Cool. So, yeah, like I said, this is like a 1-to-1. 1 mole forms 1 mole. Okay, but that's not always going to be the case. So I've been talking about what the real rate of the reaction is. So a few things about that. Regardless of what reactant or what product we follow, we're going to have to report the same rate of the reaction. So I call it kind of cleaning up or normalization, kind of like a tail end sort of thing we need to do to our delta R's over delta T's or delta P's over delta T's. Okay? So first off, the reaction, the reaction rate is always positive. So right off the bat, you can think of it as taking it times what was the reactants kept getting less, so they have a negative rate of change. So you can think of either taking it times -1, which I thought of, or you can think of taking the absolute value. Either way. Another thing here, so I'm going to try to kind of talk you through what this looks like. If you track A, which is a reactant, or you track B, which is B or C, one of the two products, you're going to have to report the same reaction rate, but they're different amounts. So I'll kind of show you how that works. Because from this, for every 2 moles of A that react, 2 moles of B and only 1 mole of C are formed. So you know that you're going to find different rates of change in the reactants, this 2, the 2A, or the A and the C. So we have to normalize it. So let's take a look at what that would look like. Now, here's another convention. Anytime you see the subscript 0, that means initial. Initial or starting up. So the initial molar concentration of A, that's what you would say. Initial molar concentration of A, 0.10 molar. We're going to go ahead and let it go for 25 seconds, which seems like a long time. And now it is decreased to 0.060. And we're going to have to be able to kind of do what we did in Chem 1, which is to say, let's see, how do I say this? This one went from 0.100, and now it's 0.060, okay? So that means that, do the difference, 0.040 moles per liter reacted. You buy that? Reacted to form these guys. So we should be able to do some stoichiometry with that value. So over this 25-second interval, let's do a little bit of math. Let's see what we can knock out the rate of change of A, which it's not too bad, right? We're just going to take that 0.060 minus 0.1 in the top, divided by 25 seconds. We have to see what we're going to do with the rate of change of C. So again, what are we going to do with the rate of change of A? It's simply going to be what it ended at, which was at 0.060, minus what it started at, which was 0.100. Again, if you want to put a big M there, that's fine too. Put moles per liter. The time interval was 25.0 seconds, 25.0, excuse me, minus 0.0 seconds. So what you're going to divide is this. So we're going to take a negative 0.040 moles per liter divided by 25.0 seconds. So we can say the rate of change of A. So now it's not the reaction rate, but the rate of change of A is negative 0.0016 moles per liter per second. That's kind of what we've done before. Now the thing about C that's different, I mentioned Chem 1, is we have to kind of figure out how much C was formed. In this case, we're going to assume that C started at 0. Okay. But here's where we say that 0.040 moles of A reacted. And now we need to use stoichiometry, so I'm looking at what? 1 mole of C formed for every 2 moles of A reacted. So this is how we're going to get the moles of C that were formed. So that math's not too bad. It looks like 0.020 moles of C were formed. Kind of Chem 1. So if the initial was 0 and that's the final, so we take, it's almost like, I don't like how I have this. So to me, instead of going right to that amount, it should be, so it's final minus initial, it should be 0.020 minus 0.000 moles per liter. Which is 0.0200. And again, the time interval, 25.0 minus 0.0 seconds. Allowing ourselves 2 significant figures, the rate of change of C over that same time interval is positive 0.00080 moles per liter per second. So if you compare the rate of change of A with the rate of change of B, or excuse me, rate of change of A with the rate of change of C, what would you say about the two? They're opposites. One's positive, one's negative. How about the magnitude? I agree.
A has a greater magnitude.
A has a greater magnitude by a factor of
Almost 3 times.
it's factor actually just of 2, factor of 2. If you take this times 2, you get your 0.0016. Yeah, factor of 2. So let's see what the catch is. Yeah, there was A, and there is C. Rate of change of A, rate of change of C. I told you that regardless of which reactant or product you follow, you have to get the same rate. So here's what we do. Oh, by the way, absolute value signs out, right? Okay. So A disappears twice as fast as C is formed, just because of stoichiometry. You had a coefficient of 2 in front of the A. So what we do for the reaction rate, or the rate of reaction, okay, is we always make it positive. That's the absolute value signs. And the second thing we do is to remove the effect of stoichiometry. This says we divide by the stoichiometric coefficient. What I usually do, though, is I multiply by 1 over the stoichiometric coefficient. So in other words, what I would say, based upon the stoichiometry of the 2A going to form 2B plus C, I would say the reaction rate would be the absolute value, be 1 over 2, that's the stoichiometric coefficient, times the absolute value of the change in the molar concentration of A divided by change in time. So I like to think of it that instead of this says basically you take the rate and you divide. It's the same thing. I just kind of like it that way. Where this is the stoichiometric coefficient. Stoich. Co. So, yeah. What I just wrote here is here. So the reaction rate, it doesn't have the absolute value of, but since it's a reactant, instead of doing that, like I told you, I can go back and forth. Instead of doing that, I went ahead and inserted a negative because it's a reactant right away. If we follow the B, since there is a stoichiometric coefficient of 2 in front of the B, we would also have to take it times 1/2. But since it's a product, we don't have to worry about any absolute value or multiplying by -1. The C, ding, 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 the C, when we came up with that 0.00008 or something like that, moles per liter per second, that was the rate, because the stoichiometric coefficient is 1 and it was a product. So, for what it's worth, that's kind of how that works. Reaction rates. They get slower and slower. Later on, we're going to only focus probably on the initial reaction rates. But so the reaction rate for this regardless of what species you track, A, B, or C, will be 0.00080 moles per liter per second. It just got to be that way. So this is kind of fun. Things happen on the macroscopic level, microscopic level, I don't know, on the small level that we just kind of blow off. And one of the things that Chem 2 looks at is kind of the behind the scenes, what's really going on. So in order for a reactant A so you have 2 particles, like A plus B goes to form C. In order for A and B to do their thing, they have to collide. I mean, we take it for granted, but they have to fight each other in the mess where they are. This is like molecule to molecule or atom to atom. They need to collide. They need to have enough energy, and we'll talk more about an energy barrier, but they need to have enough energy to actually make it work. Like if they're too wimpy, they might collide, but it's not happening. Okay? The other thing is sometimes there is like this orientation, like they have to do head to head. And if they're head to butt, it ain't happening either. So we have an orientation thing. When I start to think about these 3 things, you're surprised any chemical reactions ever happen. So how long it takes for A plus B to go to form C actually needs to take into all of these considerations. We'll be talking more about this. How long it takes, the reaction rate, has to factor in, will they collide, what's sort of frequency, how much energy do they have, and are they properly oriented? Okay, so we'll be kind of coming back to that. So I have little videos. It is Friday, you know. Collision probability, energy probability, orientation probability, well, they're right here. Okay, so You figure if you increase the concentration, they're going to be more likely to find each other. If you increase the temperature, they're going to have enough energy to proceed. That's all true. Surface area, again, has to do with the probability that the reactants will find each other. And then the presence of a catalyst, catalysts, as you may know, are reusable. They're not really a reactant. They're not consumed during the reaction, and they help with orientation. We'll talk more about what reaction orders are, but most of the reaction orders we're going to be dealing with are little superscripts, reaction orders, and they will all be positive, not negative. Like I said a minute ago, increased concentration, you're going to increase your rate. Increased temperature, increase your rate. For heterogeneous phase reactions, this would be where you have two reactants and one's like a gas and one's a solid or liquid. But surface area is a player. More surface area, faster reaction. Catalyst, I mentioned, as an example of giving us a better orientation or correct orientation. So let's take a look at these. But this is, this actually is HCl with powdered iron, and the bubbles are kind of showing how it's reacting. This is HCl with solid iron. Again, it's the surface area. This is finer particles. So this will, not to say that B won't react, it just reacts at a slower rate. And this one, excuse me, this one talks about sulfur dioxide can accelerate weathering. We'll be talking more about this too. There's a lot we'll be talking more about, right? But we talked about, or a minute ago, I said sufficient energy is a player, right? And so what catalysts do is actually allow a reaction to happen more quickly because the energy barrier is less. So what you're looking at here is along the y-axis energy, and so kind of the hump is the energy barrier. What the blue is catalyzed, and the way it does that, though, it's just amazing. Catalysts allow for an alternate behind-the-scenes pathway of the reaction. So it's pretty exciting, I think. Catalysts are pretty cool. Dun, dun, dun. So these will be due on Monday. And we are all caught up. And I will have labs, by golly, to hand back to you. This is ridiculous. So somehow, some way,